Thank you. Okay, so hello, good morning, everyone. So I'm going to start. So this lecture was the democratic will of the people yesterday on topic. So the topic that we chose to cover in the final lecture is a little bit different to the ones that we covered in the first two lectures. The first two lectures we covered divergences on probabilities, so comparing sets of objects and seeing if they're from the same distribution. And then we talked about using these divergences to train generative models. So if I have a generator, a GAN generator that's making samples, I'm comparing those to a reference sample. We're using these divergences as a loss to train a GAN, to improve the generator samples. Today we're going to switch context a little bit, and we're going to talk about causal modeling. So causal modeling, broadly speaking, is trying to figure out what happens when we act on the world. So this is really quite different to, let's say, a lot of conventional machine learning. Like if you're classifying objects, you're just looking at dogs and cats. You're saying this is a dog, that is a cat. If you're acting on the world, like you're a self-driving car. I'm going to steer left. Is that a good idea? Do I hit another car? Or I'm a doctor. I treat a patient. Is the patient going to get cured? Is the patient going to die? It's all of these questions that happen when instead of just looking at the world, we start acting on the world. And when we start acting on the world, things get a lot harder. As we're going to see, because basically, when you act on the world, context matters. And if you ignore the context, you can basically make mistakes, even if you have a very strong belief that you're doing the right thing. So this is something that we're going to explore today. And in particular, we're going to sort of talk about how to act on the world successfully. Because this is a context switch, I'm going to underline even more what I said in the first two lectures, which is that if anything's not clear, I really need you to ask me questions, okay? So this is, let's say, a reasonably challenging area, but it's also like a very rewarding one. But the main thing is that everyone should be confident that they understand what I'm saying before I go on, so that the lecture is useful for all of you, okay? So ask questions. Right. So we're going to start with a thought experiment, okay? A medical treatment scenario. So this is a hospital. And we have observed data that we've seen over some period of time. Okay, we've looked at what happens in this hospital for a particular disease. This disease can be treated in one of two ways. One is with pills, and one is with surgery. And then you can have, so that's our treatment. And then we can have one of two outcomes. Okay, the outcome is that you get cured or you get dead. Okay, and so ideally we choose the right treatment so that the patients get as cured as possible. I'm a hospital administrator, and I've looked at the historical data from this hospital, and I've noticed these two things, right? Probability of being cured, given that I've treated the patients with pills, is 0.8. Probability that I've been cured, given that the patients have been treated with surgery, is 0.72, okay? So what do I do? Pills are cheaper. So who votes that everyone from now on should get pills? No one. Who votes that everyone should get surgery from now on? Who votes that we don't have enough information? Very good. All right. So now I'm going to act on the world, right? I'm a hospital administrator. I haven't done any statistics courses. I say, OK, pills are cheap. Everyone's getting pills from now on. So now when I take an action on the world, I show that as a node with two lines around it. OK, that's the action that I've chosen to take. OK, I'm not observing anymore. I'm acting. OK. Now, y superscript a is the outcome that is in consequence of that action. So it's still a random variable. So it's only got one barrier, one border around it. But it's a random variable that happens when I've made the intervention, when I've taken the action A. OK, so superscript A, action A. Now, I've taken that action, and oh no, this is not a very good outcome, right? Suddenly, like my probability of being cured when I've forced everyone to take pills is 0.64. It's quite a lot lower, OK? Now, I could also have forced everyone to take surgery, and that's still below the cure rate for pills, but higher than the cure rate for surgery before. Okay, so what should I have done? Okay, so now we're going to look at the context. Remember that I said when you act on the world, context matters. The context here is this x variable. I'm always going to use x for context, and that's the severity of the disease. Okay, so the disease happens to have two forms: a severe form, this guy, and a mild form. Okay, now basically, the doctor, the expert doctor in the historical data, basically looked at the disease. Is it the severe form? OK, surgery. Is it the mild form? OK, pills. So pills have a good chance of curing the mild form, but they won't cure the severe form. Surgery, of course, that cures both forms, but surgery has its own risks. So, you're giving surgery to people who don't need it. They can still die from some complications from the surgery, so it's not a great idea. So now how do I get these historic data things here? Well, that's done with the formula that you see on the top of the slide here, which I'm just going to outline, okay? So basically, I want the expectation, the expected value of being cured, given that I've observed that surgery or pills were prescribed, okay? So this is the observation data. This is not the intervention data. Now, given that surgery was prescribed, I can infer that the disease was probably of a severe form. So P of X given A, well, I've seen the doctor prescribe surgery. It says, okay, the doctor looked at the patient, saw that the patient was pretty sick, and then said, okay, best surgery. So conversely, given surgery, I know that it's likely that the patient was very sick, that they had the severe form. And then I take the integral of y given AX, so probability of being cured, given that surgery was prescribed and that it was a severe form, integrated over the chance that it was a severe form, okay? Now, what if this was pills? Well, then it's probably the case that it's mild, so there's a higher probability of it being mild, and so then I take this integral over, mild given A, and this, which is high, and then like severe given A, which is low, and then this, all right? So that's how these numbers appear. Is that clear? Yeah? Any questions? So this is observational data, right? Now, when we intervened, this is this thing with the double boundary from the previous slide. And what you can see is that there is no arrow from X to that, right? I've said everyone gets pills. I'm a hospital administrator. I don't care if the patient's very sick, if the patient's not so sick. I've just made a decision that everyone should get pills. I've taken an action. Now, this action, the way that I've defined it, is disconnected from the context. There's no arrow from context to action. That means that this quantity here, so the expected causal effect of my action, I'm just integrating over the severe and mild form of the disease. So contrast that with before. Before, I was observing that the disease was mild. Therefore, it was more likely. I was observing that pills were prescribed. Therefore, it was more likely the disease was mild. And so I do this integral. Here, I'm just integrating over my entire population of patients because I've decided to act. I've decided to give everyone pills. And so this here then gives me these results there, okay? This double boundary node is not connected to X, okay? On the graph, by the way, I've kept my earlier interventional variable A. My earlier observational variable A. So this is connected to X. This is what the doctors did historically. But you can see that I've now no longer got an arrow from A to this guy because now I'm taking this action. So I can still observe my historic A's, but then this action A is connected to Y, and the historic A's are not. So I'm going to pause here and make sure everyone is on board with what I've said so far. No questions? OK. So now I'm going to go in a graphical mode and talk about the kinds of causal questions we can solve. So first is this average causal outcome, which is what I talked about here. So this is the expectation of my probability of being cured given the intervention that I've made, A. All right? But I can do something more complicated. Maybe this context variable can be split, okay? So I'm going to put another variable here called V. And this V variable here is going to be connected to this guy and this guy, okay? So I've got all of these, like X may be containing more than one context variable. So in the previous slide, it contained just severity of disease, but maybe it also contains, like, whether the patient smokes or not, how old the patient is, whether the patient's male or female, and so on, right? There's a lot of context variables. And what I might be interested in is the outcome of a treatment conditioned on this V taking some value. So it'll be something like this, E of Y, the intervention A, given that V equals V, right? What is the probability of being cured given that the patient is 22 years old? What is the probability of being cured given that they're like 98 years old, right? These are different quantities. And so what we might be interested in is like saying, well, conditioned on some of the context taking some value, what is the chance of being cured? And that's something that a doctor is much more likely to be interested in answering, not like give everyone pills and see what happens. It's like, well, what if I give pills to a 20-year-old? What will happen? What if I give pills to a 90-year-old? What will happen? Okay? So this is, in fact, in practice, the question that is more important. And it's actually the question we'll spend the most time on in this lecture. This arrow here that I've done with the 2 dashes, that means that I don't care about the causal effects within X and V, right? So I'm not interested if like V causes X, X causes V, or there's some hidden common cause that cause both, right? They're just X and V, they have some interaction. I'm not interested in trying to model it. I just know that there may be some interaction that exists. And in fact, in most useful cases, there will be. All right. Here is another funny question that I can answer. And when you see this notation, it's going to confuse you, and that's good. OK, so this is the following, right? Expected causal outcome of action A prime given, OK, that's weird, right? Now, this is actually not a stupid question. So what this means is that, like, let's take all the patients that I gave pills, OK? So historically, I gave them pills. So this is what that means, OK? Remember, this variable here is this guy, OK? Of the patients that I gave pills, what would have happened had I intervened to give them surgery, right? It's a counterfactual question. Of the patients who received treatment 1, what would have happened had I given them treatment 2? So if they're the patients that received pills, probably they had a mild form of the disease. If I gave them surgery, probably they'd be killed. Probably they'd be cured, OK? Now, of the patients who received surgery, what would have happened if I gave them pills? Probably they'd be dead, right? So these are interesting questions to explore. Like, you know, I've seen what happened when I gave patients treatment 1. Now let me think what would have happened had I given them treatment 2. And again, like if I'm a doctor or a policymaker or something like that, these are very interesting questions to ask, right? I took one decision, I got some outcome. Now, you know, this is something we as humans do all the time. Like, what would have happened had I done something else? You know, what would have happened had I set my alarm in the morning and woken up for the lecture rather than slept in? I mean, there's all of these nice counterfactual questions. We can also add additional variables to this model. So let's say that I've got a mediator, right? So in this case, you know, maybe I've given the patient some anti-inflammatory medicine, A, and then M means that they can do more exercise because they're feeling less pain. Now, how much of the effect of being cured is because they can do more exercise versus how much is the effect because of the treatment that I gave? And this is an interesting question, right? Again, like in policymakers, there are sort of downstream outcomes of the treatment that you make, which are both direct and indirect. And we're interested in like disentangling those. So how much of the effect is direct, how much is indirect? Yeah. And last of all, and I'm not sure if we'll get to that, but it's going to be interesting if we do, what happens if we don't see this, right? Now, if we don't see this, the short answer is we can't do anything because, like, you know, basically this is sort of like your, let's say a modeling effect where every cause and effect is due to some like puppet master manipulating the variables. So like if I drop this cup on the floor, it's because like a puppet master made me pick up the cup and then it has strings to the cup and drops it on the floor. So if there's a hidden common cause, then in principle, like you can't, like nothing is true. You can't believe anything. So effectively what we need is some sort of evidence that tells us enough about this thing that we're able to make some inferences about it, right? We need to know enough about it that we can figure out its effect on A and on Y superscript A. And that's something that, in fact, you can be in the situation where that's possible. And I'm going to hopefully, maybe if we get towards the end and we have some time, I'll prove to you that that is the case. Okay, if you have no evidence at all about it, then there's nothing to be done, right? There's always the possibility of some puppet master manipulating everything that you see. But that's also kind of not a very interesting hypothesis in some sense, at least if you're doing causal modeling. Okay, are there questions about what I've gone over? No, great. Okay, so first of all, I'm going to talk about this, this first thing, which is this average treatment effect or average causal effect. So this is the simplest question you can answer. This is something that's actually, like, it's very routine. But we're going to go over it because it's going to provide us the tools that we need to solve the more interesting problems. Then we're going to talk about, in my view, the most important tool of this talk, which is this conditional average treatment effect, this conditional average causal effect. This is the one where we're saying, OK, conditioned on the patient having some properties, what is the expected causal outcome? So what is the chance of being cured? All right? Then we're going to talk about this counterfactual question, like of the patients who receive surgery, what would have happened had we given them pills, or vice versa? Or what would happen if we intervened to give them pills? Then we're going to talk about these mediation effects, perhaps, which is this case where you've got both a direct and an indirect arrow. And then these proxy methods are the methods that address the case where you've got hidden context variables, but you have some information about it. So that sort of relevant information is called proxy information, as we'll see. Now, for those among you who've sort of encountered causal methods before, often you're going to see, like, this is by far the most common in epidemiological or econometrics literature. The treatment is binary, like I do something or I don't do something. But in modern machine learning, like, that's a very crude and very limiting assumption. So we're going to address the case where the treatment can be actually very complicated. So it might be like the design and placement of a web ad, or like, something that's reasonably complex, high dimensional, continuous valued. We're not just interested in treat or not treat. Likewise, these covariates, these context variables, we're interested in the case where this can be very complicated information, like web browsing history or something like that. So yeah, these points I think are very important to underline because when you assume that A is binary, everything becomes much, much simpler. But also what you can do with it becomes much more limited. And so we're much more interested in like acting in the world in complicated ways with a complicated context and figuring out what's going to happen. Okay, so that's something to underline. Okay. So now let's get into the technical matter. So there's a fair amount of like material that we're going to need before we jump into solving these problems. And so I'm going to basically start by giving you all of the context, so to speak, that you need for this. So first of all, I'm going to assume that all of the functions that I'm going to learn are linear combinations of features. So this is completely consistent with everything that we've talked about in the last previous two lectures, right? Remember, the witness function for the MMD was a linear combination of features. It was a sum of features. Likewise, all of the effects that we care about in this talk will be linear sums of features. So if I'm talking about, let's say, expectation of y given a and x, right? The expectation of y given a and x is going to be a sum of features of a and x, right? A linear sum of features of a and x. This will be true for everything I talk about. Now, whether these are neural net features or kernel features, you can do it with either. I'm going to stick to kernel features in this talk, but if you think of kernel features, just think of a fixed feature dictionary. If you think of neural net features, think of an adaptive feature dictionary. And if I'm using a neural net, all that I require is that my final layer be linear. Okay, linear final layer, everything else carry through. If I use infinite feature dictionaries, then I have to make sure that I can manipulate them only using dot products. So the dot product I have in closed form, even though my feature dictionaries are infinitely long. So a reason for sticking to the kernel notation here is because this is somehow strictly more general, right? Because I can deal with either finite or infinite feature dictionaries using this notation, whereas if I use the neural net setting, then I have to sort of stick to notation that doesn't generalize if my feature dictionaries become longer. But keep in mind, like, I'm agnostic. We can use neural net dictionaries, which we do, in fact, when we're processing images, or we can use fixed dictionaries, which we do when we're processing, let's say, wages or age or anything low dimensional but continuous valued. Okay? The key point, though, is this linear final layer. This is absolutely necessary, and we lean on that very, very heavily. Without it, nothing works, at least in this talk. Yep. Sorry, or? I mean, so one could think of it in tessellation, but in a sense, that's perhaps like it's more specific than I want to be. The way that I want to understand this is I've got a dictionary of useful features. And whether they tessellate the space or not is perhaps less interesting than whether they're good at predicting the label. Because maybe some dimensions of my input are irrelevant, right? It doesn't matter if I'm able to tile the space or not in these irrelevant dimensions. It only matters for the dimensions that are interesting in predicting my outcome. So I can have features that are very non-expressive in terms of, let's say, computing any function, but very expressive in terms of computing the function that I want. And that's all I care about. So I'm making the problem even simpler than, yeah. Yeah. Any other questions? OK. But yeah, this linearity, I mean, I can already tell you the answer. The linearity is useful because we want to take expectations of the functions as dot products of the coefficients and expected features. Remember how we did that in lecture 1? We're doing it now in lecture 3. So that is the first and only reason we're doing that. And you're going to see that shortly. Yep?
How much is this restriction in what we can model when we say we have only linear functions and features?
Yeah, so it is, in a sense, yeah, so I can repeat the question for this time. So how restrictive is it to use this linear combination? In principle, it shouldn't be, because if you've got rich enough features, you should be able to express all of the functions that you need. Yeah, so in principle, at least, yeah.
Oh, okay, perfect.
Yeah. So yeah, so basically, like, you know, with a rich enough feature dictionary, you should hopefully be able to express all the functions you need. So for example, if you remember from lecture 1, these kernels that are rich enough to distinguish any pair of probabilities, under some assumptions, these are also kernels that are rich enough that you can get arbitrarily close to any continuous function. So in principle, like, that's a very rich dictionary. You know, likewise with neural nets, like, as long as you've got a good architecture, then having a linear final layer shouldn't hurt you too much. Yeah. But you know, it is a restriction, but it's, I think, a mild restriction. Yeah. But no, that's a good question. OK. The next building block is that if we use linear combinations of features, how do we learn our conditional mean, our y-given input? We will always do it, whether we're using adaptive neural net features or not, by solving the final layer using ridge regression. So hopefully, so hands up if you've spotted ridge regression in your past. Has everyone seen ridge regression? Yes? A couple of people. OK, that's all right, because I will explain it. So basically, you know, ridge regression is actually, like, in some sense, the simplest way of predicting outcomes from inputs, right? I've got a square loss. I'm predicting y, a scalar, from a linear combination of features. But I need some way to make sure that these weights here don't blow up, don't become, like, really large, OK? So basically, what I'm going to do is I'm going to add a penalty. What is the penalty? It's just the sum of the squared coefficients. If I have a penalty which is the sum of the squared coefficients, none of these coefficients can get too big, because if they do, I will be penalized. Now you know what ridge regression is. Yep. So yeah, so it's basically like the simplest answer to the question, like, how do I regress when I've got linear functions of features? Or a very simple answer, I will say. Not, yeah. So is that clear to everybody? Now, this gamma in H notation here just means that my vector of coefficients might be infinitely long, OK? And that's OK. I have infinitely many features, infinitely many coefficients, as long as my solution can be expressed in terms of dot products of the features of your training data and the features of the new point, then we're good, right? Because I have the dot products in closed form, even for infinite feature dictionaries. OK, are there questions about ridge regression? Or that makes sense? OK, linear combinations of features, penalization by some of the squared coefficients, squared loss to compute the outcome, and that's it. OK. Now, what does the solution look like? Well, the solution, if I find this ridge regression function and make a prediction at a new x, this is what the solution looks like, right? My prediction at a new x is a weighted sum of the dot product of features of my training points and features at x. Now, remember from lecture 1, we had this exponentiated quadratic kernel. So that was the dot product of our features of xi and our features of x. I'm putting these exponentiated quadratic kernels here in red, centered on my training data points, my xi's, OK? Now, I weight these training points by alpha i's. These alphas can be positive or negative. I sum them up, and this gives me my green function. So the key point here is that if I express this solution of my ridge regression and as a vector of gamma, and I predict it at a new point, so the dot product of gamma, I can sort of write this explicitly, right? This is the dot product of gamma hat and the feature at a new point, x. Well, it turns out that gamma hat itself is a sum over I of alpha I of features of xi. You can prove that, right? A way that you can see that it must be true is because anything that isn't in that sum, when I take the dot product with all of these features of xi, anything orthogonal to the set of features of xi is just going to be 0 when I take that dot product. So you can see that the solution must be in this form, right? Anything outside of that sum doesn't help me in my prediction. Does that make sense? Okay. So given that this is a form of gamma hat, let's substitute it in, right? So let's put it in here. Sum over I of alpha I of gamma hat xi, right? I take that dot product. Now, what have I done? I've got the dot product of features of xi and features of x, which gives me my kernels. All right. So what are these coefficients? Well, these weight coefficients sort of tell me what my regression looks like. And these weight coefficients I can also express in terms of two things. One is these labels here, y, okay? Not surprising, right? The labels had better appear in the prediction. What also appears is the matrix of dot products of all pairs of features of my training points. Now, I'm not going to do the proof here, but it's a quite short proof. So if you're interested, you can pretty much look it up in any textbook. But it's like 3 lines. Basically, the moment that you know that the solution gamma hat is equal to the sum over I of the features of your training points, then this comes out immediately. You just substitute that in, you do a tiny bit of math, and then it's the answer. So it's a very easy proof. I just want to emphasize that. Okay, so this is the solution to ridge regression. And conveniently, whether I have infinite or finite feature dictionaries, it doesn't matter because I've always expressed my answer in terms of dot products. Are there any questions about that? Okay. And you can see like it's, my solution is kind of sensible. As long as I have a sensible kernel function here, then my solution is going to be a sum of those kernels. So like if I've got a nice smooth bump, my regression function will be a sum of these smooth bumps. So it's going to be a nice smooth function. Okay? So this is ridge regression, but I'm going to now rearrange these expressions in a way that you will not necessarily see in textbooks. Okay? Here is how I want to write the solution. And there's a reason for that that's going to appear shortly in the talk. I'm going to write the solution not as a sum of k of xi x with scaling alpha, but I'm going to write it as a sum of the labels scaled by beta. Now, all of these other terms are, as you've seen on the previous slide, right? This kxx plus lambda I inverse appears. This vector is the vector of kernels between my test point, x, and my training points, xi, right? That's these guys. So everything, all of the ingredients on the previous slide are here on this slide. I've just rearranged the terms, and I've emphasized that the solution is a weighted sum of my labels. Okay, same solution, tiny bit of rearrangement, but this weighted sum of labels is by far, I think, for this talk, the most crucial way to view this solution. The reason is because, okay, if these y's are scalars, then this solution is like a weighted sum of these beta i's with scalar weights. But if these y's are vectors, I can write this solution in the same form, right? If this is a vector yi, I can take a sum of these vector yi's weighted by beta I. And this is a much better way to sort of see this solution in the case where y is vector valued, rather than sort of hiding these vectors somewhere in the coefficients alpha that we had in the previous slide. So when you think ridge regression solution, this is the picture you should have in your head for this talk. Any questions? Okay, great. So this, I'm really laboring this point because it's very important, and we're going to need it shortly, so I don't want anyone to forget it. Now, for those who don't care about theory, you can check your email for the next slide. But for those who do, here is a nice result, which is basically telling you that depending on how easy your problem is, as you see more samples, the solution you get from ridge regression is going to arrive at the right answer. Okay? So what is an easy problem? There are two ways to think of an easy problem. I've got y as a function of x, so y given x. One way a problem can be easy is that y is a smooth function of x, right? If it's a smooth function, I shouldn't need that much data before I can see its shape. Okay? C is smoothness. The bigger C is, the easier my problem gets. Now, an artifact of ridge regression is that the problem gets easier as the problem gets smoother, but only up to a point. And after that, it doesn't get easier. That's just sad times because ridge regression does what it does, okay? But broadly speaking, though, at least within some range, as the problem gets smoother, the problem gets easier. Now, easier means I need fewer samples to solve it, okay? What's another way that a problem can be easy? Well, I am learning to do the regression from features. But if the covariance of these features has a very fast decaying spectrum, that's sort of like saying that my data only occupies a very small subspace of this much bigger feature space. Now, if my data occupies a small subspace, it kind of means that I'm doing a regression from a low-dimensional input. Like my feature might be 10 million dimensions, but actually only 10 of these matter for this regression problem. And so in a sense, like this means that if I'm effectively regressing from low dimensions, then my problem's easier, right? If I'm regressing from 1 dimension, it's easier than regressing from a million. And so this B basically tells me how big the space is that I'm regressing from. So big B, easier problem. So basically, the two rules. One is, if my function is smooth, my problem is easier. If I'm regressing from effectively a low-dimensional space, my problem's easier. And all of this being the case, then this tells me that my gamma hat, which I learned from data, is going to converge to my gamma 0, my true function. This is sort of saying that these vectors of coefficients are going to agree at a rate that basically depends on how easy my problem is. The very best case is that it goes as n to the minus a quarter. So basically, my error drops down as the number of training samples I've seen to the minus 1 on 4. That's, not too bad, okay? So that's my little theory indulgence. But what it's doing is it's telling you that, this ridge regression is not entirely a stupid thing to do, right? Because as I see more data, I'm going to end up getting the right answer, as long as my true function is the sum of these features. Okay. So a reason I'm showing you this is because we're going to see a harder problem later which has the same rate, and that at least surprised some people. Okay. So now all of the tools that we need are developed. Let's start solving causal effect estimation. Okay, so this is work with Rahul Singh and Lian Xu, who are here. Yeah. Okay, so let's start with, remember this case where like the stupid hospital administrator gave everybody pills. Okay, we're doing the average causal effect of a treatment A, where we're integrating over X, right? X in that toy example is the mild or severe forms of the disease. I'm going to be talking here about an example from econometrics, because the first author of the paper is an econometrician, which is an example for a jobs program for disadvantaged youths. So in this case, the A, the treatment that we give, is the number of hours of the training program that these individuals undergo. The Y is the percent employment, so what chance it is that the people who've taken this program are employed. And then this X is all of the relevant covariates, so like how much education they had before, age, whether they're married or single, so on and so forth. So all of the relevant context information we have about the people taking the program. And this, is going to both determine how many hours they can do, right? Because if they're, 16 versus 26, like the number of hours they can dedicate might be different. It will also determine the chance of success, okay? So these are the outcomes. Okay, we're making a few assumptions, okay? One assumption, I'm putting these sort of in small print here, but I can explain what they are. One is that if I give one person treatment, that doesn't affect the outcome of somebody else. So if I make you take 10 hours of classes, it doesn't mean the person who's sitting next to you gets 10 hours of knowledge for free, okay? So that's one assumption we make. Another assumption that we make is that we never ask a question about something we've never seen. So for example, what if I say, for somebody who had a mild form of the disease, what would happen if I gave them surgery? But let's say that never happened in the history of all of that hospital. Then I have no information at all. So I can't say anything about a case that I've never seen in my life. That's not unreasonable, but you have to make sure that it's true before you start making predictions on stuff you haven't seen. The final thing is that I'm assuming that there is no secret variable here that is controlling these guys that I'm not able to see. So imagine the secret variable was the severity of the disease. I would be back in the situation of my stupid hospital administrator and making the same sort of mistakes that they made, okay? So we don't want to have that happen. So we have to make sure that all of the relevant context is present, that we are able to see all of it. And we have to see all of it because we have to integrate over all of it. Okay, are there any questions about those assumptions before I go on? So they're kind of like, all of these assumptions are reasonable, like they're common sense assumptions. They're not like mathematically sophisticated or anything like that. But they have to be true, right? Otherwise you're in trouble. Okay, so the first problem that we encounter, and it's actually a quite minor one, is that we're predicting y, not just from x, but from two things, x and a. Okay, we have two inputs, and we want to predict an outcome. Now, the way that we're going to solve that is going to be familiar to you if you sat through the very last part of yesterday's lecture, which is that if we have good features on our x's and good features on our a's, then a reasonable way in which we can get a feature of ax together is just to take the product of the kernels. And that's exactly what we do here. Okay? Which amounts to using as a feature the outer product of the features of a and x. So basically, what is my feature if I take the product of kernels? Well, my feature is the product of each feature of x with each feature of a. So all of the pairwise products of every pair of features is the feature I'm using. So this is a design choice, and it turns out that it's a mandatory design choice for this work, but it may be that you have a smarter idea, in which case you can do a different approach. But for this work, we require that this is the case. Like everything that we do is going to be based on the fact that we're making this assumption. It's already a very rich class of functions, but it might, let's say try it, and if it works for your problem, then great. If it doesn't, then maybe you have to be smarter. But it's not like I'm just taking a big neural net and dropping it on a and x and getting an outcome. Like that's not possible. I can use individual neural nets on x and a, but I have to combine them by taking the products of all pairs of features. Okay? Now, if my kernel is the product of kernels, well, then that is what my ridge regression looks like, right? So what do I have down here? I've got the product of the kernels between all pairs of A and all pairs of X samples. So this is an entry-wise product. That's what this notation means, which makes sense, right? Because my kernel is a product of kernels, so this is my, yeah. And then this thing here is, again, like the entry-wise product of kernels between my training points and my test point, okay? So this is meant to be big X and little x down here, okay? And remember the form of the solution. My solution is a weighted sum of my y's. Okay, so now we've solved the problem of this having two inputs, and now we can get the average causal effect. And it's very, very easy. It's everything fits on one slide, okay? So here is, remember the average causal effect. I want to take the expectation over this random variable x, right? Expectation over this random variable x, so the mild and severe form of the disease. Now remember, my function is a dot product of these coefficients and this feature vector, which is the pairwise product of all of the features of A and X. Now here is where this outer product notation becomes absolutely mandatory, because I can take the expectation inside the dot product, and because of this outer product form, I can take the expectation only of the features of X. Now you see why we had to do that. If that was not the case, then I couldn't have done this, okay? So, this feature, this expected features of X, I've just written it down here. This is the mean embedding that you'll remember from lecture 1. So remember the MMD is the difference in mean embeddings, expected features of P and Q. Well, this is the expected feature of P. It's exactly the same mean embedding as we saw in lecture 1. So now this is sort of coming back again to haunt you. So this is the average causal effect. Are there any questions? Okay, great. Now, that being the average causal effect, by the way, we also know that the feature mean converges as n to the minus a half. That's not a surprise. I've taken a mean. It better converges 1 on root n. Okay, now here is the average causal outcome, right? I take my ridge regression solution. I take the average of that solution over all of the xi's, which are drawn from P. And remember that the average of the ridge regression solution is the average causal effect. So this is it. I'm done. It's one line. Even I can code it. It's pretty easy. Okay? And because my ridge regression solution converges at the rate that we saw, we know that the average causal effect as we see more samples is also going to converge with exactly the same expression, okay? So average causal effect, as I see more samples, it's going to be a good predictor of the true average causal effect as long as my y given a of x, can be expressed as the sum of these features. If not, it's obviously you can't get consistency. Yeah. All right. So that's nice. So let's look at the example. Like I talked about, we're going to use this for this jobs training program. So remember, X is all of the relevant information, age, marital status, and so on. A is how many hours of training. This is the outcome. And what we're interested in is, what happens if we intervene? Like I'm a policymaker, I've seen what happened in the past, and I'm saying, okay, I want all of my youths to take some number of hours of training from now on. I'm intervening on the system, I'm specifying a number of hours of training. What do I predict is going to happen? And luckily for me, I've seen all of the relevant context, so I can make this prediction rigorously. And this is what happens, actually. So the blue line is the one you should care about because this is the result of our method, but there are other methods to do the same settings, so you can also look at those. But what you see here is a nice effect, which is sort of an improvement and then diminishing returns. So you can think of this like as a student, they do undergrad and then master's and then PhD, and then they start a postdoc, and then they get faculty position and so on, right? So the positive outcome sort of rises, and then it starts to fall, right? And that sort of is reasonable even intuitively. Like at some point, these people might be in the program because they're getting some free money and they're kind of sticking around, but they're not interested in getting a job at the end of it. But up to a point, you get improvement. So this is what we actually found from this data. So this is what we predict is going to happen if we intervene with some number of class hours. So is this outcome clear to everyone? Yep, great. And this curve here, we just computed it using this expression here for different numbers of training hours. Okay, so before I go on, like, is this average causal effect clear, or is there any questions about anything up to this point? Yep.
You said that we have all the information in X, so the introductory example would not apply to this case. So in this case, we have, so in the data, they're not like lacking things. Or how do I have to understand this? We have all the information.
That's right, that's right, yeah. Like
a follow-up question, how do we make sure that we have not missed one of the causal effects?
Yeah, so there's, in a sense, like the two ways to make, well, effectively, ultimately the only way to make sure is to act according to your requirements and then to see that your predictions match the truth. And in effect, like that is the only way, right? There is no other way to falsify, have I seen all the relevant variables, than to really act on the world with all of the beliefs that you have, and then if it doesn't do what you thought it would do, then, and this is why, let's say, medical trials proceed so systematically, right? I don't want to just put the medicine on the population and hope, right? I need to do it for a small population, and if there's no bad things, then a bit bigger, and then if no bad things, a bit bigger. So that is effectively, in medicine, they have a very principled and thorough way of making sure by intervening on small populations that they haven't missed anything. And if they see unexpected effects, then it's like, okay, like my model's wrong, I haven't seen the context I need, therefore I've made a mistake. And then you quickly stop the trial before more damage is done. Yeah. But yeah, that's the answer. You need, the only way to know is to act. Yeah. Yeah. But very good question. Yeah. Any other questions? Yep.
In the previous slides, you're talking about this cosine, whatever, the product similarity. Mm-hmm. So this is a way to assess progress at the end, right? Can we do the same thing in intermediate level, in the sense that instead of the cosine stuff, just like take them outputs and calculate the covariance matrices between like both things, and this covariance matrix from an informational theoretical stuff, if the same things, if the causal stuff, they should be in the trace of this matrix, right? So in the sense that we should maximize stuff that are in the diagonal, like in the trace, and minimize the things that are not affecting our decisions, which are of the trace.
So I don't know that I follow your question, sorry. If one is thinking about feature covariances, then this is a measure of dependence. So perhaps that is what you're exploring. I mean, I think we'd have to have a whiteboard if I want to understand your question completely. Like certainly, if your question is, let me open my iPad, whether, let's say, there's dependence between x and a, then you could look at the feature covariance of x and a, like you can compute it, and you can make sure that it isn't zeros. So that sort of addresses the question of whether the x's and a's are dependent. But I'm not yet sure how to think about causal effects in terms of feature covariances. So maybe we can talk about that offline.
Sure.
Yeah.
Sure.
Any other questions? Okay. So in a sense, like the average causal effect ultimately is a rather trivial quantity, right? Because all that we're doing, it's a very, let's say, crude quantity, because what we're doing is effectively just averaging the regression function here over a distribution of context variables. But ideally, in the real world, we don't do anything that crude, right? Like ultimately, what we want to do is to say, well, conditioned on some part of these contexts taking some value, like conditioned on the age being some thing, or conditioned on the symptoms having some expression, conditioned on this, what is the effect of taking an action, right? We want to look at our population. We want to subdivide it into interesting categories, and we want to look at the effect of action on those categories. We don't want to just say, like, everyone in the world gets pills, and let's, see what happens, right? So we're going to now get to the causal question, which is, I think, at the very heart of useful causal reasoning, which is the conditional average treatment effect. So this, if nothing else comes out of this talk, like this is the thing you should remember, okay? Because this is, I think, the most powerful tool that we've developed in this toolbox, okay? So we have our context variables, but we've split it into two, x and v, okay? So we don't care about the causal interactions between v and x. We know that they probably exist, but we're not interested in modeling them, okay? Beyond what we're going to see. But we know that both x and v have an effect on our observed A, our historically observed A, and we know that x and v have an effect on our causal outcome, right? The context matters. Now, the conditional average treatment effect here is the conditional mean of the causal outcome, given that the treatment variables have taken some value, given that the age is 22, given that the person is living in some part of the city, okay? So this is the interesting question. And this is the question we're going to solve. Notice as well that we've split up x and v, and we've again used this outer product of features trick, which again is absolutely mandatory. Like nothing that I'm going to say is going to work without it. But yeah, we're going to use it here. Okay? So our regression from y to y, from a and x and v, is going to be the sum of these coefficients multiplied by the outer product of features of a and x and v. So again, the kernel is a product of the three kernels, and the features are the products of all triplets of features. So triplets of a, x, and v features. Okay, so now we want this conditional average treatment effect. Okay, so now let's substitute in our expression, right? We know that the ya given inputs is going to be this dot product of gamma and features of a, features of x, features of v. And we're taking the expectation of this conditioned on v, right? So here are the random variables. There's this x, there's this v. But I'm conditioning the v on little v, right? So, this v just takes the value little v. This x has the distribution of x given little v. But how do I take this conditional expectation? So, there are lots of ways that you could do it. There's the hard way. The hard way is to train a GAN or something, a conditional GAN, which generates samples of x given v, and then average over those samples. For each value v, I'm going to take the samples, I'm going to average over them. And this is an approach you can use, and this is an approach people have used in the past. But it's not taking advantage of what we know about our problem. what we know about our problem is that the function is a linear function of features, and that these features can be decomposed as products of features. So all that I need to do to solve this problem is to replace my features of x, given v, with this conditional feature mean, right? The easiest way to solve this problem, rather than learning a density model and sampling from it and doing the is basically just to say, well, I'm going to substitute in my conditional feature mean of x given v into this problem. Because it's linear, I can take this expectation inside my dot product. Remember how important linearity was at the start of the talk? Now you can see why. Remember how important it was to take these products of features? Again, now you can see why. I can take this expectation inside, and now I have this conditional mean of features of x given v. So because of the assumptions that we've made, linear final layer on one hand, outer products of features on the other, I now have actually a problem that I can solve by regression, rather than by a much harder problem of density estimation and sampling. So this is, in a sense, like the heart of the tools that I'm talking about today. So is that clear to everybody, or are there questions? Oh, yep.
So does it also work if you know that V exists, but you can't condition on it because you don't have observations, but you want to do missing value type of inference? Or is that completely useless in this causal analysis?
There is ways. That's a very good question with a very involved answer. In the case of unobserved context variables, it's still possible as long as we have variables associated with those context variables. At the end of the talk, I have some slides on that. If we don't get to them, I'll show you in person. But you do need, in a sense, like with no information, you can't say anything. The question is how much information? And that's, there is,
see,
yeah.
Age is an extreme case. Mm-hmm. If the patient doesn't want to give you his age or her age, well, yeah, bad luck.
Yeah.
But lifestyle is an assessment thing.
Yep.
And the patient might misjudge it, and you might actually want to question and have an inference procedure to sort of correct for that.
Absolutely. So yeah, we can, I mean, there's like ways to explore. So one way, which is to do with like anonymization, is like sensitivity analysis. I'm not going to tell you my ages. I'm not going to tell you my age. I'll end there. However, I can say that my age is somewhere between 30 and 50, let's say. Okay, or maybe a narrow interval. And so in this case, we can say, well, okay, in that case, the range of outcomes you might expect is such a range. So this is a sensitivity analysis. Or I can sort of say, inference is a good example. That's fun. That's an interesting iOS bug. So another case is, as you say, like somebody might, have some claim about their lifestyle, like their spending patterns. But what they say and what they do might be two different things. They might say, I'm very frugal, I only eat vegetables, I drink water all day, but you can sort of smell the cigarette smoke on them, and And so that's, so here, of course, we have indirect information about the V, which then gives us some sort of confidence interval around our outcome. So absolutely, like there's all of these settings. So here, when I mentioned indirect context, that context is that the doctor looks at the patient and says, like, okay, you're not jogging 10 miles a day. I can see that this is not what you're doing, or and so on. Or you say you're not smoking, but I know that you're smoking, or I can guess that you're probably smoking. And so this is where this indirect information is very helpful. So this is how one addresses this case where V is not observed without error, but it's sort of like inferred, or you can get it up to some amount of anonymization detail. Okay, are there any other questions? Okay, but no, these are good questions, and causality, like the whole point of it is to make useful conclusions from data, and so these are questions you have to ask. Like you can't assume that you're in an ideal situation where everything's perfectly observed, even though that's what I'm discussing today. To deploy this in practice, you need to really think hard about your assumptions and make sure that you're not assuming away the information that you need to get the answers that you are after. Okay, so basically, here is the problem that we're trying to get. if we can learn the conditional feature means, the features of x given v, then we have our answer. Then we're done. Like, after that, it's completely trivial, okay? The question becomes, how do I learn a conditional feature mean? So the unconditional feature mean we learned. We took samples from x, we take the average of the features, and that's all it was, right? But now we need a conditional feature mean, okay? Now, if v took one of two values, it would be easy. I just gather all the data with v equals 1, gather all the data with v equals 2, compute the two different means, and then I'm done. But what if v is a continuous valued variable? Or what if v is even more complicated? This can happen, right? I can have a very complicated v. In that case, I need to do something with machine learning. I can't just like break my data into two and do half on one, half on the other. Okay. So let's see now how I can compute the conditional feature mean. And then once I've computed it, everything becomes easy. Okay. So here is the problem. I want the conditional feature mean. Now, I want to compute this, or I'm making the modeling choice that I'm going to compute this by taking the features of v and multiplying them by a matrix, which is a v, dv times dx dimensional matrix, to get out the features of x. Now, I use the word operator here because it could be that I'm using infinite feature spaces, in which case I need to make sure that everything is in terms of dot products. But whether it's finite or infinite shouldn't matter to me, okay? So I take my features of v, multiply by matrix, get features of x. Now, because I'm taking this form, I know that my solution is going to be, in effect, a sum of outer products here of features of x and features of v, okay? Because I know my input is features of v, output is features of x, so my solution has to be basically like a sum of outer products of x features and v features. That will give me the right dimension and the right sort of matrix space. Now, I need some notion of smoothness. This notion of smoothness is that the sum of the squared singular values of E are finite, okay? Now, remember when I did ridge regression, I said the sum of the squared coefficients are finite? This is the same thing, but for matrices, okay? So basically, everything I'm doing is kind of taking ridge regression, saying I have a matrix, and then doing everything the same as I did before. But please interrupt me if that's not clear. Okay? Now, what's interesting is that if I make this assumption here, that amounts to saying that the conditional mean of any feature of x given, any function of x given v is a smooth function of v, okay? Because it's expressed in terms of the features of v. The features of v are smooth features. I'm making this smoothness constraint. That means that if I take the conditional mean of any function of x features, given v, it's going to vary smoothly with the input. That's a smart assumption, right? Because if my function varied arbitrarily quickly with my input, then no amount of data would allow me to learn it. If my function varies smoothly, then with enough data, I'm gonna learn it eventually, because I've got a nice pattern, and I can sort of impute what is going to happen between the training points that I've seen. Okay? So we call this E a smooth operator, because it gets smooth functions. Okay, so how do we learn it? We learn it using ridge regression. No surprises, right? This looks exactly the same as the scalar ridge regression. Scalar ridge regression had a gamma here and a gamma here, but now we're mapping from features to features, so we've got a matrix here and a matrix here. This is the norm that I talked about here, the sum of the squared singular values. It is exactly the same as the sum of scalars squared that we used in ridge regression. It's just for a matrix rather than a scalar. Okay? So basically, I said at the start, all you need to know is ridge regression. That remains true, even if we're looking at a matrix or an operator rather than at a scalar regression. Okay? So we solve this with ridge regression. Because we solve it with ridge regression, right, up here, what does the solution look like? The solution is a weighted sum of the features of the output, weighted by the betas, which are exactly the same betas as for the scalar case. So all that happens, before I had here y, here is a y, now I have the features of the output. I have a weighted sum of features of the output. So remember I said at the early part of the talk that I'm going to write ridge regression in a form that you're not necessarily used to from elementary machine learning, which is a sum of the scaled output, scaled by beta. Now you see why I did it. I did it because it shows that whether the output is a scalar or a vector of features, it's still a weighted sum of the inputs with the exact same weights. So despite the fact that we're now regressing to a vector of outputs rather than a single scalar output, nothing changes. okay? So this is giving my conditional feature mean, basically using exactly the same toolkit that I used to get my conditional y given a and x. Okay? Here, remarkably, let's say the smoothness is the same. Like I'm saying that my regression is from a smooth function of the v's, and the smoother the function, the easier it gets. So that's C1. I'm saying that if my input features have a small subspace, then my problem's easier. That's B1. And then I get exactly the same convergence rate as I had before. So basically, this matrix converges to its target matrix at a rate that depends on how hard my problem is. If my output is a smooth function of my inputs, it's easier. If I'm regressing from a small space, it's easier. Okay? So the same things that made scalar regression easy also make regression to vectors easy, right? It's just like how smoothly does my expected value of my features vary with my inputs. This is when I said that like people are surprised. Like this is a result that at least was initially surprising to us because we thought, okay, we're regressing to infinite feature spaces. Like surely that's harder. But it so happens that under the assumptions that we've made, and in particular this assumption that we have this smoothness on our problem here, it's just as easy as the scalar case. So I'll pause here in case there are questions. All right. So this is valuable because, we don't want to just apply this without knowing if it's going to work. But we've proved now that it's going to work. Like as we see more samples, our prediction of this conditional feature mean is going to get better. Now all that's left is to substitute the conditional feature mean into our regression, right? So this is a regression from our treatment, our context that we don't condition on, the context that we do condition on, to the outcome y, right? Now, we've specified our treatment. Okay, we've specified the number of hours of training. We've specified the value of the context. We've specified the individuals are of age 22, let's say. And then here, we're regressing to the conditional mean of the rest of the context variables given the context that we've seen. So given that the person is like, let's say 16 years old, the probability of them being married is low. Given that the person is 33 years old, the probability of them being married is higher, right? So if X is the chance of being married and V is the age, then we know that given a certain age, we know something about the rest of those variables, right? They're likely to have some values. If the age is 16, it's less likely they have a PhD. If their age is 40, it's more likely they have a PhD, and so on, right? So that is what we do here. And then we integrate over the X's, given that V, to get our Y. So it's no longer the unconditional mean, but it's now the conditional mean. Okay, so this is the conditional average treatment effect or conditional average causal effect. And again, it's just one line, okay? So there is nothing that one needs to type in to implement it besides what you can see on the slide. Okay, and again, because my regression from A, X, and V to Y, and the regression from V to features of X converge, we know that our average causal effect is going to converge as we see more samples. So we basically inherit the good properties of the building blocks that we use to build this thing. Okay, so now let's look at the example. So this is, again, this job data set, and I kept talking about age. So indeed, that's what we're going to condition on. We're going to say, like, if we intervene, if we give some number of hours of training to people of different ages, then what is going to be the outcome? What do we expect to happen when we make those interventions? And here is the contour plot that we get. Okay, so on the x-axis, we have the number of hours of training. On the y-axis, we have age. And what we can sort of see, we can slice this at different ages. So we can sort of slice it at age 18, we can slice it at age 22, and we can sort of look at what happens when we give a certain amount of treatment to people of different ages. So for 16-year-olds, employment increases from 28% to 36%. If you're 22, it increases from 40 to 56%. So this is useful. Like if I'm running this program and I have a limited budget, it's like, how do I allocate my funds optimally so that I get, let's say, the best or the largest number of people getting the best possible outcome? This is effectively what I'm able to sort of measure by looking at these graphs. I'm sort of saying, well, I've observed what's happened in my training program previously. I can sort of see, I can make predictions about the actions and what might occur at different ages. And then I can say, okay, I'm going to allocate a lot of my budget to 22-year-olds because I can sort of see that there's a big uptick in their employability for our training. And so that might be the outcome that we take. Okay, questions about conditional average treatment effect? Right. Yeah, so basically, this is, I think, the tool that is, of all of the tools that we have, this is the one that hopefully you're most likely to use in your day-to-day lives, right? Because you're sort of saying, I'm working at a company, I want to figure out, this ad program, what's its effect going to be, but I'm going to break down the impact by demographics, right? So, in advertising, you always have, people of age 22 to 25 who are interested in sport, who, live in such and such a city, et cetera, right? This is a tool that you need to solve those problems. But essentially, the sort of key point is that you can solve them even when the treatment is something that isn't just binary, like on or off, but it's something that can be more complicated. Okay, so now we're going to do an exercise together, which is the counterfactual, right? The average treatment on the treated. So this is where you start getting really into the more sophisticated aspects of causal reasoning, which is that you start running thought experiments that never could occur in real life. So I can't, if I gave somebody a pill, I can't take the pill out of them and then give them surgery. I can't do that. But I can make the thought experiment. I saw what happened when I gave you the pill. Now what would have happened if I intervened to give you surgery, right? So it's not something I can do, but I can make the thought experiment, and then I can say, okay, this is, maybe in future, this is what I should be doing for patients of that kind, okay? So yeah, this is, I think, a very valuable tool to have. And we're going to show on this slide how easy it is to do that. So I'm going to work through this example live. So hopefully not make too many bugs, all right? So this is the tightrope walking part of the talk. Okay, so I've got the gamma 0, which I take the dot product of features of A and I'm going to use a smaller eraser. There we go, features of A and features of X. Now, by the way, I didn't mention, but the features of A and X could be different, right? There's no reason to use the same features for context and for treatment. So basically, the argument of my feature tells me which feature I'm using, just to keep the notation simple, all right? So I know I have a linear function of the outer products of these features, which is to say the pairwise products of all features of A and of X. Now let's substitute this in, okay? So I've got basically here the conditional mean, right? And now let's substitute in. I've got my gamma 0, right? I've got my features of the random variable A, right? And my features of the random variable X, right? Conditioned on, oops, let me close the bracket, conditioned on the A taking the value little a. I already made a bug. There we go. I fixed the bug. Okay, so I'm saying that I'm making the intervention A prime, but I've got my random variable X, which is conditioned on A. Let's look at this on the graph, because this is going to help us to reason about this. I'm making the intervention A, right? This is the action I'm taking. There's a direct arrow for that to the outcome. There's also an arrow from the context to the outcome. But there is no arrow from the context to the little a, right? I'm just taking that action. I'm not looking at the context. I can't even see it, okay? However, I'm conditioning on patients who historically had the treatment little a, right? Now, if they historically had the treatment little a, remember that I left this historical value, this historical random variable on the graph for a reason, right? If I know that the patients historically had treatment little a, that means I can say something about the x, right? If my patients historically had had pills, I can reason that the form of the disease is probably mild. If historically they had surgery, I can reason that the form of the disease was probably severe, right? So this random variable here is dependent on this historical random variable here, okay? So conditioned on the fact that the patient had pills, what would happen if I gave them surgery, okay? So this is the what would happen question. This is what happened in the past. Is that clear? So these counterfactuals kind of mess with your head a bit, so that's why I'm making very sure that everything makes sense. Now, life gets very easy, right? because now I take the expectation inside the dot product. Remember, linear final layer, outer products of features. So now I get this, right? I've got gamma 0 dot producted with my feature of my intervention, A prime. And then I have my conditional feature mean of my features of x given A, right? So, how severe was my disease given that I saw that I had surgery? And then I've got this guy here, right? There we go, we've solved the problem. So that's pretty nice. Okay, now here is my next challenge. I'm going to attempt to write the solution in terms of kernels. Yep. There's an opening bracket missing.
The round bracket after A is where is the opening?
Here. Yeah. Yeah, my handwriting is appalling. Yeah. Yeah. So conditional feature mean of x given the historic A being little a. Okay. Now for my next trick, I will write this entirely using kernels in a way that you can implement. And it turns out that it's quite easy, right? So I've got my y's, my labels, right? And now, what am I going to have? I'm going to have this multiplied by, well, I'm regressing from A and X, right? So I've got like K, A, entry-wise K, X, plus lambda I inverse, right? Now, I've got my treatment, my intervention, A prime, right? But now I need to regress from the conditional feature mean of X, right? So now, rather than having, if I was just doing average treatment effect, I would just sum over the x's. But because I'm doing this conditional one, I need the conditional feature mean as my input. So I've got this kxx, and then I've got kaa plus lambda 2. Let's say I'm using a different lambda. I inverse ka little a, right? All of this stuff here is basically from the conditional feature mean of x given a, right? So this is sort of to show you that once you have the trick, you can just write down the answer with very little thought by plugging conditional feature means into these like second stage regression. So I sort of take an input conditional feature mean, and I get a second stage regression out of it. So are there any questions about what I just did? So this is really nice because, this is, in a sense, the highest, if you have seen Judea Pearl's tutorials, so he's a Turing Award winner who won the award for his work on causality. He calls these counterfactuals like level 3 of causal reasoning, like the highest level of causal reasoning, because I'm making conjectures or I'm making thought experiments about things that never could occur in the world but are interesting for me as a human, like reasoning about how the world works. And so, these sort of counterfactuals are of that nature. Yeah. But, as a policymaker, these are useful. I did something, it didn't work so well, so then what could I have done? Like, what should I do in the future? That's the kind of question that I'm answering here. Okay. And I actually have these also on the slides in case I screwed up. Okay. So now, let's end by doing the final example. I think in the time that we've got, because we've got more or less 15 minutes, right? Yeah. Is that right? Yeah, it ends at 12:15? Yeah, okay. So I think the good one to end on, I won't do the hidden variable one because that would take more than 15 minutes, but I'm going to do the mediation analysis one. The hidden variable one's on the slide, so you can read it yourself later. So remember that mediation is when I've got two paths in which A could affect Y, right? I've got a direct path, right? But I've also got an indirect path. The example from this job training program, in this case, the mediating result is the amount of employment. So that used to be my Y, now it's an M. And now my Y is the chance of being arrested, right? So there are both a direct and an indirect path. If I've done the training program, maybe that makes me directly less likely to be arrested. Or I've done the training program, therefore I'm more likely to have a job, therefore I'm less likely to be arrested. Now, if this path is the stronger path, then maybe it's better to just make sure that people get employment, like help them to get employment, rather than having them do this training program. If this is the most important path, then the most important thing is to make sure that the training program is done, right? So, you know, when I'm looking at the effect of my actions on the world, it's important for me to, you know, basically determine whether the direct or indirect path matters, because that will in turn determine how I choose to act in future, right? Based on the data that I've seen in the past. Okay, so now, you know, my function is a function of 3 inputs. So this is the y given its inputs. There's 3 paths to y, right? There's the path from x to y, the context. There's the path from m to y, the mediator, and then the direct path from the treatment to y. Okay, and I want to find out whether this path or this path is stronger, or whether both paths matter, which, you know, in many real-world cases is the case. Okay, now to do this, we need to ask a very, let's say, sophisticated causal question, which I'm going to explain. But this is definitely one where, if anything's not clear, you have to ask me, because it is a very messy kind of quantity that we're about to compute. Okay? This effect is called the mediated effect. And there's a lot of notation going on here, but that's kind of unavoidable in this case. Okay? First of all, there's the direct effect of the treatment. And I'm going to call that, you know, the direct effect of the treatment A prime. Okay, so this is basically like I'm making the treatment A prime directly affecting the y. Okay, but if I make a treatment that also changes the distribution over m, right? If I've done a certain number of hours of training, that changes the distribution over employment. Okay, so what I'm going to do is I'm going to express the distribution over employment as if I had done another kind of training, little a. Okay. So basically, I'm changing this distribution in a way independent of the way that I'm affecting directly my outcome. And that's kind of cool, because I'm saying, well, you know, I'm having some direct effect, but my m is changing as if I did something else. And that way, I no longer have the correlation between a and m. I'm allowing m to shift in ways that are not affected by the direct intervention on y. Okay? So, you know, let's say I'm doubling the number of hours of training, so that has a direct effect on chance of being arrested, but I'm also, let's say, dropping the amount of employment, as if the people had only had like 1 hour of training. Okay, so I'm changing the distribution of employment independently of the action that I'm taking on y. I'm saying, like, let's pretend as if we stopped everyone from getting jobs, but they still had to do the training program. And, you know, that way I can determine, well, if I stopped everyone from having jobs, what if they still didn't get arrested? Well, then my training program was great. If I stopped everyone getting jobs, but I still made them take 1 million hours training, and they all got arrested, then maybe my job program is not so smart, and I should actually make sure that people are employed. So does this rather complicated thought experiment make sense, or are there questions about it? So this is the hardest counterfactual question you're going to encounter in this talk. That's why I want to pause now. Yep.
But so the kind of combination of A and M, we're not focusing at all, because it could also be that there's somehow correlation between having making this training course and getting a job.
Yep.
So we completely leave out this path of the graph.
Yeah. So basically, you're absolutely right. There is you know, let's say there's the correlation of the training program and getting a job. There's a correlation between the training program and the outcome of being arrested, and there is the correlation of the employment and getting arrested. So all 3 effects could occur. Okay. So in a sense, you know, the intervention that we're exploring is, well, it's a sort of 2-part intervention. One is, from now on, you know, what would happen if we forced everyone to have this amount of hours training, okay? So that accounts for the direct connection, the direct correlation between training and arrests, okay? However, we're also saying what would happen if we shifted the employment distribution as well, right? And we want to shift the employment distribution and see the effect of shifting M on arrests, right? However, we can't shift the employment distribution arbitrarily, because in our training distribution, in our training data, in our historic data, the way in which we shifted M was by adjusting A. So we can only shift it, in the ways that we've sort of seen in the past, which is indirectly by adjusting A. So we're sort of saying, of the set of, we see on one hand the set of plausible employment distributions, and on the other hand, the set of plausible direct outcomes. But what we want to do is say, well, what if the training was, 10 hours, but the employment was as if it would be if I did 20 hours. So way more employment, but way smaller training. We're still modeling both effects. What we're breaking is this sort of coupling between A and M. So historically, the number of hours training determined how much employment. Now we're sort of saying, what if we had way more employment and way less training, or way more training and way less employment? What would happen? Yep?
Okay, thank you.
Yeah, no, I'm very happy you asked, because it took me a long while to figure out this stuff. And when you look at the expression, it's not clear at all. But the thought experiment, once you explore it a little bit, it becomes clearer. Okay, and not to sort of hide the punchline, what you can do, once again, is to express all of this in terms of regressions and conditional feature means. So it's basically as easy as before. If I had time to waste, I could write down the kernel expressions. They're very simple. But basically, I'm mapping from Y, features of A prime. Then I've got my conditional feature mean of M given green A, and then my features of X, right, which I marginalize over. OK. And so this is how I get this rather complicated mediated effect. This is, again, like something that policymakers really care about, because maybe this course is super expensive. Maybe everyone should just get better job hunting support. Or maybe, this course is so good that the people don't get arrested having done it, and whether they go on to be employed or whether they go on to do something else is less important in terms of getting the final outcome. Okay? So we've actually done experiments on this for this job data set. Now, I'm going to show you two results here. Okay? This result is the total effect. So in this result here, I do not decouple M from A. Okay? So basically, I make just one intervention on A, and then that intervention is the same intervention on M as it is directly, right? So I use the distribution of M as I would with A prime, and I also do the treatment A prime directly on Y. Okay? So at this point, no decoupling. This is basically like, I don't care if it's direct, indirect, whatever. I just want the total outcome. And what I'm doing here is I'm comparing two interventions. I'm comparing intervention A prime with intervention A. What that is like, if I did two interventions, is one intervention better than the other? Is it worse than the other, right? And so what you can see here is that if A prime is 1,600 hours, okay, so a bigger amount of class hours, versus A is 480 hours, then that actually has a big improvement. So if I had a choice between two interventions, one was 480 and one was 1,600, I would choose this if I wanted the best impact, right? If I wanted the biggest reduction in arrests out of those two. Okay? So that's already interesting. Like, I'm comparing two interventions, and I'm figuring out which of the two would give me the better outcome. Now let's go into this thought experiment, which is, again, it's like a counterfactual. It's one of these things that can't occur in the world, but you can use to understand how the system works. Okay? This quantity here is as it was before, with basically the direct and indirect effects both taking the same intervention A. Now here, though, we're decoupling. Okay? We're using an intervention A prime, but we're not shifting the employment distribution. Employment distribution is as it would be for 480 hours, but the amount of training is now much, much more. Okay? So I'm decoupling my employment distribution from the number of hours of training that I require. And then, sadly, if you look at these two graphs, they look the same. What that means is that there is no significant indirect effect for this data. So basically, the reduction in arrests in this case comes from having done the course, and there's no, let's say, additional indirect effect coming from the fact that the people have more jobs. So that's kind of interesting. It shows that on this data set, the course is what matters. And the course has two positive outcomes. One is that you get more jobs. The other is you get fewer arrests. But you don't get, let's say, a separate additional bonus from the fact of having more employment. Yeah, it's pretty much, the whole effect is the direct effect. Yeah. Mm-hmm.
So can this be explained when you go back to your formula?
Mm-hmm.
The formula allows you to set A and A prime to be the same.
Yes.
But the derivation of the formula assumes that they are independent. And so the formula might actually compare a case which is not what you just described verbally, because the coupled case would not have this formula.
What I'm going to do is I'll write down the intervention graph, because I think that will help the discussion, answer the question. Let's see. So what I'm going to do, I've got my x here. I've got my a here. This is the original historic a. I've got my arrows to y. Right. Now here is where things get a little messy. I've got a prime. And this should have, I'm going to just zoom in so I can draw it, a double boundary around it. And then I've got A, and this should also have a double boundary around it. Okay. Now the A prime has a direct effect on Y. The A has the effect on the mediating distribution, right? So if I show this, and then I go down to Y.
I see this situation, but it implies that A is not equals to A prime.
So these are interventions. So I could set them equal or not equal, right? I'm just choosing them. I'm saying, like, I'm making an like, these have no parents, right? The A and A prime. And so I can set them. These are choices that I make, right? So in effect, I'm saying, like, I'm requiring from now on, I'm making the intervention that Y has treatment A prime, but I'm also making the intervention that M has the distribution that it would have if I gave it treatment A. And these are choices that I'm just making a design choice in my model. I'm setting these things in advance, and then I'm seeing what would happen.
So what you're saying is, if you always would use A equals A prime,
right? Yep.
You still can treat these A prime, the first A prime and the second A prime, independent as your formula says.
Right, yes.
Okay.
Yeah, that's right. That's exactly right. Yep. Yeah. No, the reason I didn't put this graph in the slides is because the software that I was using to do these graphs didn't support this double intervention. So yeah, but now you can see it. All right. So this is, in the sense that, what we were hoping was that there was both a direct and an indirect effect. But actually on this data, there isn't. We've also, of course, made some synthetic data where it is, but we had a lot of hope for this jobs data set, and sadly it didn't turn out the way we wanted. One very fun thing you can do, and this is actually in epidemiology, this is the common approach, is that, in epidemiology, like in a hospital, right, you don't just give treatment once, right? Particularly for complicated and chronic diseases, you give a sequence of treatments, right? And the sequence of treatments both affect the treatments you give in the future and the covariates in the future and the final outcome of the disease. So a famous study using this kind of graph is treatment for AIDS, because AIDS is a chronic disease, and so you need to basically give like a sequence of treatments as a way of making sure you get a good final outcome. And so in this case, you can use exactly, like the formulas start to get a little bit messy, but it's exactly the same sort of story as we talked about before. We get these conditional feature means, we get the outcomes from these conditional feature means. You can also ask some very interesting causal questions, like, what would happen if we did this intervention or that intervention or a combination of interventions, or counterfactuals, where, of the patients who receive one treatment or one sequence of treatment, what would happen if we gave them another sequence of treatments. So everything that I talked about in these models, which are non-sequential, I can generalize to the case of sequential models. So models where you have a sequence of treatments, each of which affects the patients in future times, which in turn affects the treatment that they get in future times, and so on and so on. So in medicine, this is the kind of scenario that people are often in, because that's what happens in real life when you're treating a complicated disease. So I sort of put this graph here just to sort of show you the complexity of the kinds of interactions that we're able to model using the tools that we've talked about today. And this is in the paper, but I won't put the formulas on the slide because it will just look like a big pile of matrices. Okay, so unobserved confounders, sadly, that will be for another time. I want to sort of mention that the slides that we've put online have all of these papers that talk about all of these things. The code for everything should be online. So this is the case where we've got visible context. So these two papers are sort of covering what I did today. And then these papers here are covering what happens when you've got hidden context, but some information about it. And so all of those are also online. All of the software is online. So these ones in particular, implementing them is really tough. So don't. Instead, download our software and don't save yourself the agony. Yeah. Great. OK. Oops. So that's a good place to stop. So thank you.